Well, hello everyone. How's my audio today? How's my sound? Can you hear me?
Yeah.
All right, thank you. Okay, guys. Well, today what I want to do is we have one more problem to finish. We didn't finish from last lecture. I have the problem on the board. I want to talk about the last problem on the handout from last lecture, and I want to start something new today. We're going to talk about magnetism. We'll start magnetism today, and then we'll finish it. We'll finish it on Monday. Also today, I want to say at the end of the lecture, I'll talk a little bit about the exam, the one that you submitted, and the one there's going to be exam 3 posted. So I'll say a little bit about that. So if you have a second, get the document from last class. Also, there's some documents I put on a blackboard about maybe 20, 30 minutes ago. You don't need to print those out now, but these are documents available for the magnetism lecture. So at some point, you want to print those out. And have those ready. Probably do some stuff with it next time, but if you want to have the topic sheet in front of you, that might be kind of handy. So if you have the handout from last class, it's the one titled Capacitors, a Few Interesting Circuits. I want to finish that up, and then I want to review capacitors. There's another sheet, a capacitor review. I want to briefly go over that once we get done with the problem on the board. So if you have that sheet out, take a look at it. I've reproduced the problem on the board, and this one is called a burst of energy. A burst of energy. Well, when we began our discussion of capacitors, I kind of drew a parallel between capacitors and voltage sources. You know, a capacitor, a battery, both of them can provide voltage, but the difference is a battery can provide voltage for a long period of time. Capacitor can initially provide a voltage, but then it's going to discharge through whatever load it's connected up to. So you might wonder, well, what good is a capacitor? Well, one advantage we mentioned that the capacitor has over just a regular battery is you can charge a capacitor up really fast. You can charge it up extremely fast. The other advantage, or another advantage, is you can get what we call a surge current out of it. If we need a lot of current in a short amount of time, as this problem will show, you can do that. And there are applications that require that. As a matter of fact, when we get into magnetism, we'll talk about one such application. So if you have the handout, take it out. If not, I'll put it on the board. The problem statement called a burst of energy. The first part of it, they want to know what is the maximum current when S1 is moved to position 1. So right now, we assume that the capacitor is uncharged. The switch, this is a 3-position switch, is in position 2. I call that the neutral position. And we're going to move it to position 1. So the question is, what is the maximum current when S1, I don't have it labeled S1, the switch is S1. What is the maximum current when S1 is moved to position 1? So take a second, get your calculator out if you think you might need a calculator. And I want to know the maximum current in the circuit when the switch is moved to position 1, from position 2 to position 1. Let's see if you can figure that out for me. Just to review, we talked about the universal time chart for capacitors, and you know the values already in the graph. You know that this is our steady state. So that's going to be here. It's going to be our 9 volts for this circuit. We call that steady state. When the capacitor charges up to the source voltage here, we say it's a steady state. And you know, for voltage, the voltage across the capacitor is going to charge up like this. Real fast at first, and then the rate a charge is going to slow down, slow down, slow down, but eventually it'll reach the 9 volts. It'll reach steady state. At that point, it'll stay at a constant 9 volts as long as I don't do anything to it. And you also know that it takes, for this to happen, it takes 5 time constants for that capacitor to fully charge. But we also talked about last time the way current behaves in the circuit. Current is always decaying. So at t equals 0, when I move this switch from position 2 to position 1, at t equals 0, the current, because this is V or I, the current's going to start off right here. So that's going to be max current. And then it's going to slowly decay. And after 5 time constants, the current is going to reach 0. So the question is, what is the maximum current in the circuit when I move the switch from position 2 to position 1? And the maximum current is going to happen at t equals 0. I get maximum voltage across the resistor, therefore I get maximum current in the circuit. So at t equals 0, remember, the capacitor is a short circuit. So at t equals 0, all you have in the circuit is this battery, that resistor, and this is a short circuit. So all the voltage, as you know, is across the resistor. Therefore, my maximum current is going to be 9 volts, which is all across the resistor, divided by 1 k ohm. So my maximum current is going to be 9 milliamps. And again, that happens right here at t equals 0. T equals 0. So if you have the sheet out in front of you, what is the maximum current when the switch is moved from position 2 to position 1? In this case, it's going to be 9 milliamps. But I want you to make sure you understand the graph. Initially, all the voltages across the resistor, the capacitors are short, so the maximum current is going to be the resistance divided, the voltage divided by the resistance. In this case, 9 milliamps. All right, so the next question is, how long in seconds will it take C1, I don't have this label C1, but how long will it take the capacitor to fully charge? So they want to know how many seconds is it going to take that capacitor to fully charge. So don't answer, just go ahead and calculate the answer and then we'll talk about it. So we moved the capacitor, the switch from position 1 to position 2, and now we're going to wait for it to charge up. The question is, how long will it take to charge up? To figure that out, we first have to figure out the time constant for charge. So the time constants for charge, I need to go ahead and label this. It's just going to be the product of R and C. And you know from before that we call that tau. So tau for, I'm going to call that tau C for charge. And that's going to be the product of R times C. And we showed you in the other video that when you take the product of R times C, you actually do get time in seconds. So for R, I have 1 times 10 to the 3rd ohms. For C, I have 10 times 10 to the minus 6. And the unit, remember, for capacitors is a farad. So you go ahead and do the math for me. When I multiply this, I'll put it up here. I get 10, and I multiply this. I get times 10 to the minus 3rd seconds. So it looks like tau for charge is 10 milliseconds. Now that's not my answer because they want to know how long does it take to fully charge, and the answer is it takes 5 time constants for that capacitor to fully charge. So I got 10 milliseconds times 5. Take 50 milliseconds for the capacitor to reach steady state. In this case, 50 milliseconds to reach 9 volts. So if you got that as an answer, then you're good to go. Questions so far with what we've done? This is really just kind of a review. But what I want to question, what I want you to look at, now remember that the maximum current, I'm going to put it up here in the corner, the maximum current was 9 milliamps. I'll just put that right here for now. So remember that. And we said it took, 50 milliseconds to fully charge. So you guys remember that number. And let's look at the next part of the problem. Here's where this gets really, really interesting to me. Notice I have a light bulb here. A light bulb, incandescent light bulb has a filament in it, just a little piece of wire that heats up when you pass current through it. And the resistance of that wire is 0.1 ohms. So here's a situation where when I'm in position, I go from position 2 to position 1, I'm charging through 1,000 ohm. And once that reaches 9 volts, once it reaches steady state, I can go from position 1 to position 2 and I can hold that charge. I can basically hold that voltage. What I'm going to do next is move it from position 2 to position 3. But remember, this capacitor has charged up to 9 volts. So it now has 9 volts across it. This capacitor is going to act like a voltage source. And when I move this to position 3, it's going to dump current that way. It's going to light up that light bulb. But notice I charged up through 1,000 ohms, but I'm discharging through 0.1 ohm. That's a really common thing to do. So what happens when I do that? What happens when I do that? Well, look at C. If you have the sheet out, they want to know what is the maximum current when the switch is moved from position 1 to position 3. Now we're assuming that we let this thing completely charge up to 9 volts after 5 time constants. Then we move to position 2 and we hold it there. And now we're going to move from, well, they says from position 1 to position 3. So it's in position 1 for 5 time constants. This is charged up to 9 volts. And now we're going to move it over here to position 3. I went from a charging circuit to a discharging circuit, but I'm discharging not through the 1K, I'm discharging through that light bulb of 1 ohm. Let's see what happens when we do that. So we want to know the maximum current. But before the maximum current was, remember it was 9 milliamps. Let's figure out what the maximum current is now. See if you can calculate the maximum current. That'll be the maximum current for discharge. Anybody get an answer?
Is it 90 amps?
Exactly. It's not. You hear that? 90 amps. So how do we get that? Well, this is for discharge. We're discharging. This is I max for discharge. You got 9 volts, just like before. But this time we're discharging through a much lower resistor value. The filament of the bulb, 90 amps. Now I know you guys may not have an appreciation for current. Milliamps, we deal with milliamps. 1 amp is a huge amount of current. Your heart can stop with milliamps. 100 milliamps is enough to stop your heart. You'll feel it at 10, 15, 20 milliamps. You can feel a shock. And once you get up above 100, 200, now we're talking about fatal levels of current. So 1 amp is a huge amount of current. Maybe a car starter might take 10 amps to turn that motor over. That's a huge amount of power. We're talking about 90 amps. That's a hell of a lot. We went from 9 milliamps, 9 thousandths of an amp, to 90 amps. Here's where a capacitor soars over a battery. You can't do that with a battery. I mean, that's a huge amount of current. So if you ever, that's what we call a surge current. I mentioned that word earlier, a surge current. Well, here's a surge current. Here's a surge current. Now, you might think to yourself, well, hold on a second. You mean you can have a little itty bitty capacitor. I can see out of that capacitor, I can see out you can get 9 milliamps out of that. That makes sense to me. But are you saying you can take a little itty bitty capacitor, little tiny capacitor with little wires hooked to it, and get 90 amps out of it? Yes, you can. But there's a trade-off. Let's figure out what the trade-off is, and that's the next part of the problem. Now remember, it took 50 milliseconds for this capacitor to charge up through the 1K resistor. So now they want to know, for the last part, how long will it take in seconds for the capacitor to fully discharge? How long will it take to fully discharge? So give me an answer. How long will it take to fully discharge? How would you figure that out? You got to take tau. Now this is a discharge. It's not the same as charge, because now we're discharging through this. But our RC time constant is going to be, this is the R now, 0.1 ohm. And we're going to multiply that by 10 times 10 to the minus 6 farads. And when I multiply this, I'm going to get 1 times 10 to the minus 6. Now, this gives me seconds. So that's a microseconds. But remember, it's going to discharge in 5 taus. It's going to discharge. So it's going to take 5 times 1 microsecond. It's going to take 5 microseconds to discharge. So who can tell me what the trade-off is here? Why did they were able to get a huge amount of current out of this little bastard? What's the trade-off?
It's the capacity of the a battery has a much higher capacity than a capacitor for voltage.
Okay, but the question I'm asking is, how is it that we can get 90 milliamps out of a little bitty capacitor? I wish I had a capacitor to hold up, because it might be the size of your fingernail.
It's basically
And 90 amps is a huge. It's basically what?
All at once. The 90 amps comes all at once as opposed to spread out.
Exactly right. Now that, who is that? Is that Sam?
It's Ethan.
I couldn't tell by the voice. Yes, Ethan. Now, Ethan is exactly right. Now pay attention to what he said. He said basically this is all at once. Think of it like this. This is a really bad example, but this is the only one I can think about. Imagine you had an Olympic-sized swimming pool. Let me erase this. You got an Olympic-sized swimming pool. Here's your swimming pool. But this swimming pool is special because it has a trap door at the bottom of it. It has a watertight trap door at the bottom of it. You pull that rope, it opens up. And what you have over here is a spigot. And you're not going to turn the water on, you're just going to let that water drip in. Now, I know if you think about it, we said it took, what was it? What was the charge time? Was it 50 milliseconds? I believe it was 50 milliseconds. I can't remember if it was 5 or 50, but basically this water dripping in is like this thing charging up to 1,000 ohms. Now, I know a millisecond to you is like really fast, but to current, it's like a year. If it has to wait 5 milliseconds or 50 milliseconds for some, the electrons are sitting around bored. It's like a whole year. So this water's dripping in. That's the charging through the 1K. And then when I get the swimming pool full, the capacitor's full at 9 volts. When I open it up, I let all the water out at once. So it's the same amount of water, but the water went in really slow. So I kind of spread that energy out over time. And then when I took energy out of the capacitor or here the pool, I let it all out at once. So that's the point of this, a huge burst of energy. If you ever need that, if you ever have to have what we call a surge current, this is a surge current, the capacitor is the way to go. And I don't know, it used to be when they had the, I don't know what you call is it SLR cameras, the photographer cameras. You'll see the photographers now have the big the flashes on the cameras, and the flash, when you take a picture of something, the brightness of that flash is directly related to the current that goes through the bulb. And if you open up a regular camera, the battery is just a little, could have one of those little coin batteries or maybe a battery pack, but the batteries are not that big. Definitely cannot provide 90 milliamps. But what they do is they'll actually take a bank of capacitors and charge them up. I had a camera that had a big flash on it. You can actually hear the capacitors. Zzz, capacitors would charge up, and then when you press it, you're charging it up through a large resistance, so it takes a while to charge the capacitors up. That's why you can't just machine gun the flash. It won't take flash after flash after flash. You take a picture, you got to give it a second to charge up. So you're charging up through a high resistance, relatively high resistance. But when you push the button, you're discharging through a really, really low resistance light bulb. So you get a huge amount of current, which gives you that bright flash of light. Now this turns out to be really, really, really useful. You probably can't right now, but I can think of a lot of applications for this. And I'll show you one when we talk about magnetism, where this works out really, really well to make something called a rail gun. We'll talk about, if you ever heard of a rail, if you haven't heard of one, we'll talk about it, you will. And this actually works really well for something like that. So this is a pretty good problem because it demonstrates a lot of the principles we talked about for capacitors. But that finishes up the sheet, a few interesting circuits, and go back and look at this because there's a couple of really good problems here. If you have the sheet in front of you, let's take a look at it for a second. The very first problem at the top of the page, if you have it, I don't know if the camera will pick this up or not. It's on Blackboard, but if you have this sheet out in front of you, exam 3, I'm gonna borrow some stuff from this sheet and put it on exam 3. So if you have this sheet in front of you, the very first problem we did, there's a 9-volt battery and there's 1, 2, 3 resistors and a 10 microfarad capacitor. And that's the one where they want you to calculate VC, the voltage across the capacitor, at 2 tau and at T greater than 5 tau. And the problem is we had never done a problem like that before. Anytime we did an RC circuit, at any given time, that capacitor was connected to one resistor. It charged through one resistor or discharged through one resistor. But on this problem, you have a whole network. You got 3 resistors there, and that capacitor hooked up to it. And how do you do a problem like that? Well, the way we solved it is, if you remember, we Thevenized the problem. If I give you, well, not if, when I give you the exam, if I give you a network of resistors and I say, all right, give me the voltage across the capacitor or the current to the capacitor at a certain time, and there's more than one resistor, and it's a series parallel circuit, the only way you can do that is to Thevenize it. When you Thevenize it from the point of view of the capacitor, then you change that from a multi-resistor circuit down to a regular RC circuit like we've been working since we've been talking about the subject. So that was the point of the first problem. The second problem, it says find the voltage across each resistor at 2 times, 2 special times, T0 and T greater than 5 tau. Now you want to remember those 2 times. If I have a DC circuit with capacitors and I say T0 or T equal to 0, that's the instance I close the switch. And when you do your analysis, what you got to do at T0, capacitors are equivalent to a short circuit. And so what you do at T0, take your circuit, redraw it, remove all the capacitors, replace those capacitors with shorts, and then you got to stand back and look at the circuit to see if those short circuits those wires are taking anything out of the circuit. You got to be really, really, really careful with the short circuit. A short circuit in parallel with anything takes that anything out of the circuit. And then it says, all right, well, let's do the same calculation, but this time T greater than 5 time constants. What 5 time constants? The capacitor is equivalent to an open circuit. So for that analysis, you would redraw the circuit and open up every capacitor. Erase, take all the capacitors out of the circuit, leave an open circuit in the place of the capacitor. And there, if I have a capacitor in parallel with something and I open it up, it's not going to affect it. But if I have a capacitor in series with something and I open it up, then whatever that capacitor is in series with, it's not going to get any current anymore. Won't have a voltage drop, so it's going to affect the circuit in that way. So both of those problems on that sheet are titled "A Few Interesting Circuits." Problem number 1 and problem 2 were meant to drive home those points. The first one, given the multi-resistor network, when you're trying to find VC, you got to Fibonacci the circuit. And the second one, we did a couple problems like this. At t equals 0, you know, capacitor behaves like a short. 5-time constants or greater, you know, you replace capacitor with an open, and then you do your analysis. And then there was this problem where I just wanted to show you one advantage of using the capacitor is I can get a huge amount of energy out of it. Here, energy in the form of a current. There's a big difference between 90 amps and the 9 milliamps it took to charge it up. 9 milliamps charge it up, but it took us, I think it was 50 milliseconds. I can't remember if it was 50 or 5, but it took us milliseconds to charge it up. It took us microseconds to discharge it. So we got a huge burst of energy. We can actually do something with all that energy at once. There's applications for that. So this is a really, really, really good sheet to review before I give you exam 3.
Hey, Ron, I got a question. In problem 2, you gave us these two t equals 0 and t equals greater than 5 time constants. What if you gave us a t equals 2 time constants? So you have 2 capacitors in there. Would you do like to solve that? Would you have to do like superposition or what would you do?
Well, first of all, I know that's Steve. First of all, I wouldn't do that to you. I wouldn't give you that. But to answer your question, that's a little bit that problem. There's I don't know if you guys, but you really would want to use calculus and differential equations when you're doing some higher level calculations like that. And so with the algebra that we have, I don't think I would give you a problem like that because it makes the solution to be a little bit beyond you. But you can use differential equations and you can use some calculus to solve that, and the solution is not too bad. The problem is with you guys, you don't have to have a calculus prereq for that. So you know we don't do any of that in this course. Now in AC, I do borrow some topics from calculus. You guys don't have to take calculus, but I borrow some topics from calculus because I need that to explain certain things. So we're not really doing calculus, but I'll borrow some concepts from it, explain it to you, and then I use that explanation to explain some AC stuff. So if you take AC from me and not the other guy, you'll see that. But here, you're asking for a problem where we have to pull out some high-powered mathematics to do that. So I don't think there's an easy way to do that.
Okay, that's helpful. Because I couldn't figure out, I was trying to figure out, well, you can't use you can't Thevenin's it. Treat it like a voltage source or something.
Yeah, see, you probably had Diffie Q, so yeah, that's a Diffie Q problem there. So that's a little more than, I like saying this, that's beyond the scope of this course for right now. We'll just put it that way. Anybody else have any questions? That was a good question.
And just to, like you said this, but I didn't hear the whole thing. You said if it's an open like a circuit, the things in parallel, they're not affected, and the things in series are affected, right?
Yeah, so what I was saying there is, and I'll be honest with you guys, that's on exam 3, that's one of the, let's see, my Thevenin problem is missed a lot. I don't know why. And then the one that Kevin, I think that's Kevin, just asked about, even though I'm going over it, people miss it. I know why they miss it. You guys miss it because you don't understand what a short does and what an open does. So either you do or you don't. If you understand it, you'll get it right. If not, then you're going to have issues. So what I was saying, Kevin and anybody else that's interested in that, is that if I have I'm going to draw the whole circuit. But let's say I have this. I got a voltage source, and I'll give you a resistor here, a cap here, and a cap here. So I have that. Maybe I'll put a resistor here. When t equals 0, what does that circuit look like? Well, at T equals 0, everything that's a capacitor is going to be replaced with a piece of wire. So when you replace it with a piece of wire, what I was saying was, if you have imagine you have a resistor here. Let's say it's 1,000 ohms. And here's your ohm meter hooked up. Here's a wire, here's your meter. You're looking at that meter, it's reading 1,000 ohms. While you're looking at the meter reading 1,000 ohms, somebody comes in here and takes a wire from here to here, that reading is going to change to 0. Because you have 1,000 ohms, think of the wire itself as a resistor with a value 0. You have 1,000 ohms in parallel with 0 ohms. So basically, it takes it out of the circuit. So when you come over here to do the analysis on exam 3, once you replace this with the short, ask yourself, okay, is that short in parallel with anything? Because if it is, whatever is a short with in parallel, I got to take it out. But right here, this isn't in parallel with anything. So when I take it out and replace it with a short, all that's going to do is connect that resistor to that wire. Not going to do anything else. What about this one? Now that one's a problem, isn't it? Because when I replace this with a short, look what happens. When I replace this with a short, that short is across this resistor, so it's out of the circuit. But not only that, it's across this resistor. Both this resistor and this resistor are out of the circuit. So the only resistor in the circuit, I should have labeled them, but it's this one. Can you see what I'm saying? This short takes this out and this out because that short is in parallel with this branch and this branch. Well, if I put the capacitors back in there, and I do the same thing, but now I'm going to open up the circuit. So at T, not 0, but T equals 5 tau or greater. Now this isn't open, so no current, no current can go through, let's say that's R1, R2, R3. Current can go through here. When I open this up, that doesn't affect anything. It only affects the one that the capacitor was in series with. No current can go through the open circuit, so that resistor doesn't get a current, there's no voltage drop across it. The path the current is going to take is this way. So for T5 tau, this is what the circuit looks like. So given this on the exam, capacitors in series with something, when I open them up, whatever they're in series with, it's out of the circuit. R2 here is out of the circuit. If I have something in parallel at T0, whatever they're in parallel with is out of the circuit. That's only at T equals 0 because it's a short. A short in parallel with anything is going to take it out of the circuit. So if you don't get that, go back, and I forgot which video it is now, but go back and watch that.
R2, if the circuit is in short, R2 is not counted?
Let me see. What did I have here? I had this. Yeah. I had that. Did I have a capacitor here?
No.
Yeah. Is that what I had?
No, I'm asking about R2. When the capacitor are in a short.
Yeah.
R2 is not in the circuit.
At T equals 0, this is, let me label these so you can, so this is R1. I think this is the one you're talking about, R2. And this is actually a resistor, R3. So at T equals 0, then this is a short. So, yeah, that's in the circuit. Now, I don't know if I might have drawn the circuit another way. I thought I had a capacitor over here in parallel with it. Right now, as it is right now, then R2 is in the circuit because that short circuit, all it does is connect the resistor to the bottom part of the circuit. So as it is right now, yes, it's in the circuit. But I think before I might have had a capacitor in parallel. Like if I do this, even if I keep that there, but if I do this, that's where the problem comes. If I put a capacitor right there, well, right here, when I replace that with a short, that resistor's in the circuit right now. But then over here, what happens? That's a short. That short circuit is across this branch and this branch over here. That's a short and this is a short. So that capacitor's right there, that short's going to take this whole branch out and this whole branch out. The only resistor in the circuit would be R1. Now you got to be crystal clear on that, because again, that's where students have problems not understanding that. It was the same thing when you Thevenized. Remember you Thevenized? I gave you a Thevenin problem, and I put the voltage source in the middle. And when if you remember that one problem I gave you the voltage source. I think it was something like this. You had a resistor over here, and I think you had your voltage source in the middle. I don't remember the exact problem, but it was something like this. And then you had a resistor here, and maybe I don't remember. You might have something. Let's put another resistor, and maybe that's your load. I don't know. I'm just making this up as we go along. So maybe that's your load, and you want to Thevenize this. But when you Thevenize this, when you want to figure out RTH, you open it up. But then you got to take this voltage source and you got to replace it with the short. And when you replace it with the short, that short's going to take this resistor out of the circuit because it's in parallel with it. So you got to be able to see that, or you're going to run into a problem. So I don't know. If I don't want to use too much time on this, but if that's not clear, what I would say is, send me a text, and if you guys want to make up some problems or something and have me draw them on the board and we can work them out, we can do that. But you got to make sure you understand that short open circuit thing. Not that bad once you get your mind around it, but for some reason students have an issue with that. So I don't know if I answered your question or not, but you can ask me again. You can ask me more. After this is over, I can keep the camera rolling and you can ask me more questions. Okay, let me go over this other sheet real fast, and then I want to get into magnetism a little bit, and then we'll finish it up on Monday. So I made you a review sheet, the points that we talked about that are important to capacitors. So what I would say is the problems that we did on that few interesting circuit sheet, make sure that you feel comfortable with those, and then make sure you understand the concepts on this capacitor review sheet. These are on Blackboard. You probably printed them out already. So the first one, number 1 through 8, I'll just read those real fast and make sure you understand the concept or the principle. Number 1 says capacitance is the ability to store charge. Even though it's storing charge or energy, we think of it as just storing voltage. Well, stores charge, but charge is separated its voltage, so we can think about it as storing voltage. So capacitance is the ability to store charge. A capacitor is a device that we use to store the charge. So the difference between the term capacitance and capacitor is 1 and 2. The unit for the capacitance is a farad, but microfarads and picofarads are most common. Physically, capacitance depends on the area of the plate. Now we're talking about a parallel plate capacitor here. So physically, capacitance depends on A, D, and K, where A is the area of the plates, or area of one plate. D is the distance between the plates, and K is what we call the dielectric constant. There's also a little fudge factor in there, but for the most part, just think of K as a dielectric constant. So we went over that in some detail in the video, the earlier video on capacitors. So go back. It's on Blackboard. You can rewatch it. It's on YouTube. You can rewatch it, and it'll be a good review for you to do that. Electrically, capacitance depends on Q and V, where Q is charge and V is volts. So that's your formula. I call that the Ohm's law for capacitors. C is Q on V. Number 6, capacitors store energy in the electrostatic field that is developed between the plates. We really didn't talk a whole lot about the physics of it, and we don't have time to go into it, but if somebody's really interested in that, I'll be happy to, once we're done talking, I can keep the camera on, and we can talk about a little bit more about the physics behind the capacitance. I know one thing that I mentioned, I didn't really go into it, is How is it that when you take the dielectric out and put another one in, how does that increase or decrease the capacitor's ability to store charge? And that's an interesting topic. So if somebody's interested in hearing about that, you can let me know. I can make a video, or we can, as I said, we can keep the camera rolling and talk about it. Number 7, it says the ideal capacitor. What is an ideal capacitor? If I had a perfect capacitor, it says the ideal capacitor has no resistance and does not dissipate power. Now, that's not important for what you guys are doing now, but when you take AC, it's going to be very, very important. That idea that a perfect capacitor does not dissipate power. That comes up and turns out to be pretty important in AC. And then number 8, the practical capacitor has a small amount of resistance. And then it asks the question, where does it come from? Well, the actual capacitor, if you think about it, I have a conductor and a conductor, and I got a lead. And so that lead, remember R sub W, rho L over A, resistance of wire? That's a little tiny piece of wire. And on the bottom plate, I have a little tiny piece of wire. So both of those add resistance to the circuit. Also, I got some kind of way I got to glue or weld. I got to cement the wire to the plate. So there's a contact resistance there. So I got resistance in the wire, and I got that contact resistance. So I actually do have resistance in the actual practical capacitor, but the resistance is so small, most of the time you can ignore it. It's kind of like having $1,000 in one pocket and 2 cents in the other pocket. You don't think about the 2 cents. Now, sometimes this is important. I'll mention in AC. Again, if you take me for AC, we get into a lot of physics stuff. It's mathy and physicsy. I don't know what the word is. It's mathy and a lot of physics in it. And at least the way I teach it, I go into a lot of this stuff, so it gets to be kind of interesting in AC. But then this can make a difference in certain cases. And again, that's an AC thing. So if you're not taking AC, don't worry about it. If you're not taking it from me, don't worry about it, because they probably won't go into that. If you take it from me, we'll dig into that, because to me that's fascinating, and how this comes up and it can actually affect certain problems if the frequency's right. But we'll get into that if you take AC. So that's the first A review. That was all the review part of the sheet. Now at the bottom was more like a topic sheet, and I'm just going to go through it real quick, and then we'll get out of this and we'll move on to magnetism. So if you have this sheet out, this is titled Capacitor Behaviors. And here I have it written down a little differently. Number 1, it says capacitors have 3 phases, 2 DC phases and 1 AC phase. There's a typo there, but it should say 1 AC phase. So here I have the charge-discharge phase. And in that charge-discharge phase, it's really 3 parts to those phases. There's the T equals 0 part. There's a part where it's actually charging, and then there's the steady state part. So at T equals 0, the capacitor is a short circuit. This is if it's charging. At 5 tau, it's equivalent to an open circuit. And then while it's charging, we call that the transient time. That means things are changing in the circuit. What's changing? Well, the voltage across the capacitor is changing. It's going up if we're charging. The voltage across the resistor is changing. It's going down. If we're charging or discharging, the voltage across the resistor is going down, and the current is always decaying. Whether we're charging or discharging, the current is always decreasing. So all that change going on, they call it the transient time. Transient means change. So those are the phases for DC. And then there's a steady state phase. So once that capacitor is fully charged, it's going to stay charged. It's going to maintain that charge forever in an ideal situation. And then C, if you have the sheet out in front of you, there's a word here that says AC reactance phase. What the heck is that? Well, it says that's for next semester. When you take AC, or whenever you take AC, we'll talk about something called reactance. Capacitors have reactance in AC. It turns out that reactance is a kind of an opposition, kind of like resistance, but different. And again, if you take me for AC, you get into the physics behind that. I say that because a lot of people teach this. If you teach it from an engineering point of view, we talk about reactance, we give you the equation, and then you use it. But from a physics point of view, you want to know, okay, what's really under the hood of the car? this stuff happen. And that's kind of the way I teach AC, is from that point of view. So we'll get into what is reactance and what, how's it different from resistance, and we'll get into the nuts and bolts of that. But anyway, that's another class. And then I go into charge discharge phase, proof that R times C is equal to time. If you take the product of RC, you get time. We showed you that. Now here's something interesting. 2B, if you got the sheet in front of you, if you ever thought about this, now think about this. Think about this. If this is an insulator, we said that's a dielectric, that's an insulator. If I hook up a switch and a battery to this, when I close the switch, if I have an ammeter in here, let me put an ammeter in here. Let's say I put an ammeter in there. When I close that switch, current's going to flow into the capacitor. I'm going to get a reading on that ammeter because of the way the graph is. If I'm reading current, that's an ammeter. Current's going to go real fast at first, and then it's going to slowly decrease until that capacitor is fully charged. And when it's fully charged, the current's going to stop. But if I have an insulator in between here, how is it that current is flowing through the circuit? Because you can't get current, you can't get charge through an insulator. So how does that happen? Well, it turns out there's a really kind of interesting solution for that. And I'm just going to quickly say that before you charge this capacitor up, there's an equal amount of positive and negative charge on the plate. There's a neutral. The plates are neutral. There's an equal amount of plus and minus charge on the capacitor. But as you start to dump charge for every positive, now I think a current is a flow of positive charges because we're talking about conventional current. But for every positive charge you put on the plate, it pushes one away on the bottom. Now how does it push it? Well, even though you think of electricity as particles of charge moving, even though those particles of charge cannot move through the insulator, the dielectric, what can move through the dielectric is the electric field. So imagine it like this. Imagine I have instead of charges moving, what if I had little bitty magnets moving? And as you'll learn here in just a second, magnets are just like charges. If I have a plus and a plus charge, they repel. A minus and a minus, they repel. Well, magnets, we have a north and a south pole. So if I have a north and a north, they repel. A south and a south, they repel. A north and a south, they attract. What if I have a pole here, a magnet? I can move a magnet here, close to here. Maybe that's a south pole. If there's another south pole here, the magnetic field can go through the material and push the other one away. So the pushing is done here by the electric field. So even though there's no current flowing through a capacitor, current does actually flow in the circuit until that capacitor charges, and the force to push that charge on around the circuit comes from the electric field, and it can go through the dielectric with no problem. I don't know if you got that or not, but just keep playing the video over and over again, and hopefully it'll sink in. Anyway, that's really not important for what we're doing. To me, it's just interesting, so I added it to the list. Usually stuff I wondered about when I was in school, I'm kind of adding it because I'm thinking, all right, maybe they wonder about that. Let's see where else. So I was 2B, no current can flow through a capacitor because it's a dielectric. No current can flow through it. Charge is accumulated on the plates of the capacitor. So I accumulate positive charge on the top of the plate and negative charge on the bottom plate is the way we think about it. So as that current flows in there, the charge just kind of piles up until the charge on the capacitor or the voltage on the capacitor equals the voltage from the voltage source, and then everything stops. I'll reach what I guess you can call equilibrium condition, and then the current stops. Let's see. As charge is accumulated, the intensity of the electrostatic field increases. Just saying, as I put more and more charge here, the electric field that exists between the plates, it gets more intense. When the capacitor is discharging, all voltages and currents decay. I don't know if that's right. It says exponentially. I don't know if that's exponential decay or not. I got to look in my math book. I know when it builds up, that's not an exponential build up, because an exponential build up looks like this, right? That's an exponential build up. So I don't know if decay is exponential. I got to go off on that. So I don't know. I'm going to put a question mark by that one. But basically, it happens quickly is the point that's being made there. And then H, it says KCL always applies. Actually, not only KCL, KCL and KVL. On any circuit I give you with capacitors or anything, Kirchhoff's voltage and current laws must apply. So just remember that. That could help you. And then the very last thing on this sheet, the steady state phase. A fully charged capacitor acts like an open circuit. You know that. A fully charged capacitor acts like an infinite resistance is another way to think about it. Ideally, an open circuit and an infinite resistance are the same. Either way, a current cannot flow through an infinite resistance. A current can't flow through an open circuit. And you know that to get current is V over R. Well, if I have an infinite resistance, that's going to be 0. So that's all that's saying. And let's see, the last thing here, there's a typo there. It says steady state analysis, and it has the word replace. I don't know, I must have fell asleep when I got to that point. I left the whole sentence off. But what should be there is steady state analysis, replace all capacitors with open circuits. If I'm at 5 tau or greater, replace with open circuits. If I'm at t equals 0, replace the capacitors with short circuits. With a short circuit, if I'm between T0 and 5 tau, I got to use those transient analysis equations that we put on the board last time. All right, so that was the capacitor sheet, and that was a lot. Anybody have any comments or questions before I move on? Because if you don't, we're going to move to a completely different topic. All right. Well, it is, we got about maybe 30 minutes, so we got time. I kind of don't like when these videos overlap. I like for each video to be its own thing. But on this one, we finished up talking about capacitors, and we're going to move into a new topic called magnetism. And I actually called the name of the video Magnetism. So if you go back and you're reviewing, you got to kind of remember that this is the tail end of the last video. We didn't get finished. So this is the tail end of that where we finished this capacitor stuff. But I want to talk about magnetism. Now, you want to take notes for this, so I can't see you guys. But make sure you're writing this down. Well, the first thing you should ask yourself is, you didn't sign up for that. Why the heck are we talking about magnetism when you sign up to study electricity? This is DC circuits, not DC mag. Why are we talking about magnetism when this is supposed to be a circuits course? And the answer is quite simple. It turns out that you can't talk about one without talking about the other. They're like two sides of the same coin. If you have a current, you cannot have electric current without having magnetism. You cannot have magnetism without having electric current. If you got one, you got the other one. And since they're so closely related, we got to talk about it. Now, the interesting thing about it, and I don't know the dates, I used to know the history stuff back when I had more time to study stuff like that. But for a long time, the early scientists or early, they're called natural philosophers, they were aware of electricity or electrical phenomena, and they were aware of magnetic stuff, but they didn't know that the two were related to each other. For a long time, they thought they were two separate things to study. And then one day, this guy, I might be 17 or early 1800s, this guy was walking with a compass, a compass to find direction, and he walked past a wire that happened to be hot, was carrying current. When he got really close to the wire, the needle moved on the compass needle. The compass needle moved. He was like, well, what happened there? He stepped back, and the needle went back to north. He got back over by the wire, deflected towards the wire. And that was the first time that scientists realized there was a connection between magnetism and current. So if you're taking notes, here's what I want you to write down. I'm not going to write down everything, but what I want you to write down is this. All magnetic fields, the cause of all magnetic fields is electric current. The cause of all magnetic fields, any magnetic field, is an electric current. So what I'm saying to you is this. If you could put on some special glasses and see magnetism, if you see magnetism anywhere in the whole universe, someplace, somewhere, there's electric current creating that magnetism. Now, don't forget what current is. Electric current is charge in motion. So what I'm saying is charge in motion creates a magnetic field. If I have charge and it's sitting there, I don't have a magnetic field. If I take the charge and I move it, I now have a magnetic field. If I have charge and it's stationary, I have an electric field. All charge, whether it's positive or negative charge, has an electric field. But if that charge is stationary, I have only electric field. If I take the charge and I move it, I still have the electric field, but now I have magnetic field associated with it. So any moving charge creates a magnetic field. Here's the thing, though, that's interesting. And this is more of a physics thing. Here's something that's cool. If I have charge and I move it, it creates magnetism while it's moving. If I stop it, if I stop the motion, the magnetism goes away, but the electric field is still there. But I don't have to move the charge. There just has to be relative movement between me and the charge. So I can have the charge stationary and I can move away from it. If I move away from it, the fact that I'm moving, I still see a magnetic field. Now that's something that can make you scratch your head and just kind of go crazy if you think about it. So there's relative motion. I can actually take the charge and move it, or I can move and see the charge moving, and I get either way I get magnetic field. That's some relativity stuff. So we won't get into that. But what I want you to write is all magnetic fields are created by charge and motion. Write that down if you start notes. All magnetic fields are created by charge and motion. And what I want to do is talk about two types of magnetism. Really, there's only one type of magnetism. But let's see, two ways we can get magnetism. That's probably a better way to say it. The first thing is something that everyone is aware of, a permanent magnet. You've all played with permanent magnets. You've seen them. When you drew those pictures when you were a kid, those little pictures with the crayons, your parent probably took the picture and stuck it on the refrigerator with a magnet. So you've all dealt with magnets and you know what they are, and you played with them before. You know that, as I said earlier, you can take the two magnets and turn them one way and they push apart, and you turn them both the other way, they push apart. But if you leave one like this and one, then they come together. So unlike gravity, that force between magnets can be a force of attraction or repulsion. And so on a magnet, we have poles. We have poles. So when I talked about charge, we have plus and minus polarity for charge. Well, with magnets, we don't have plus and minus. We have a north and south pole. So I'm going to draw this magnet with the north pole and the south pole, and this is just a simple bar magnet. That's a bar magnet. So I have a north and a south pole. Well, over here, if I have charge and it's separated like that, you know that that's voltage. But also you know that in the region between this charge is electric field. So I draw the electric field like this. And we understand the electric field to have direction and magnitude. So I'm drawing the electric field like that. That's the electric field, E field. Well, we have exactly the same thing around the magnet. We have a field that I can draw like this around the bar magnet. It's going to look like this. And I don't know if you can see this in the camera, but I'm drawing arrows on here because it comes out of the North Pole. So it comes out of this way and goes around into the South Pole and actually goes through the magnet like that. So I'm going to draw just a couple of these. So if I have a bar magnet, if I have electric charge, I got an electric field that exists between that region of positive and negative charge, and it may look like this. If I have a bar magnet, I have the same kind of a field, not electric, it's a magnetic field, and I have it spreading out like this, where it comes out of the North Pole, kind of comes around and goes into the South Pole, and continues through the magnet. And I want you to notice a couple things about the way I have this drawn. Number one, at the ends of the magnet, at the poles, at the North Pole and the South Pole, these lines, let's call these lines of force. Lines of force. These lines of force are more scrunched together at the poles than they are out here. They spread out when they come away from the poles. That's one thing to note. The second thing to note, well, you probably can't notice it, but I'm just going to tell you, these lines of force, they can get really, really close to each other, but they're not allowed to cross each other. So if I have, a regular, I'm drawing with 6 lines here, you might have 100,000 actual lines of force. And by the way, you can actually see this. Don't do it now. But I know when I was in probably 7th or 8th grade, they took a magnet and they took like some paper, put the magnet under the paper, and then you get a piece of metal and you file the metal and you shake it around. And what you'll see on the paper is the outline of this field. So when we're done with the video today, if you go on YouTube, you type in something like magnetic field iron filings or something like that, you'll see it. It's probably somebody on there doing the experiment. You can actually see these lines of force. You can see it. So now there's some terminology that goes with this. So that's kind of what I want to spend the day talking about. We'll run out of time. I want you to get the terminology. And then we'll pick up on it on Wednesday. So we already talked about these lines of force. Well, these lines of force have a name. They're called flux. Flux. So these lines of force represent magnetic flux. And there's a symbol for magnetic flux. And I'm going to draw the symbol. You can draw it like this or like this. I like that way for some reason. I don't know why. But sometimes this is quicker to draw. That's actually the Greek letter. Is it phi? Phi, whatever it is. That's the Greek letter. But we use that. We use R for resistance, V for voltage. We use this for flux, magnetic flux. So that's the symbol we use for flux. Now let's talk about units for flux. One unit, well, before we get into the unit, remember when we talked about systems of units? So we had units. And we had the English. And over here, we had the metric. And over here, if you remember, we had CGS. And we had MKS. And just in case you forgot what this means, this is centimeter, gram, second. This is meter, kilogram, second. So there's these two subsystems under the metric system, CGS and MKS. And the reason we have two is sometimes we measure things that are like really, really big, relatively big. Well, we'll use meters for that. MKS, meters or kilometers. If I measure something really small, I would use centimeters. So I got centimeters, which is small compared to a meter, gram, which is small compared to a kilogram, and it's seconds is seconds, so there's no big deal there. Now I'm saying that because I'm going to give you the unit for flux, but I'm going to give you a unit for CGS and a unit for MKS. Pay more attention to the MKS unit, but it is important still to know the CGS unit. So I'm going to give you both of them. So what I've talked about so far is you got a bar magnet. You've all played with bar magnets before. I'm drawing this field around. It's called a magnetic field. The magnetic field consists of lines of force. The lines of force have direction. They come out of the North Pole, come around and go into the South Pole. We said that they're more concentrated at the poles, which should make sense. They're all entering or leaving on the ends, so they're more concentrated at the poles. I also said that those lines of force are not allowed to cross each other. They can get really close, or they can spread out, but they cannot cross each other. And so the group together, we call that flux. So this new term is flux, or magnetic flux, if you want to be strictly correct. And then we said there's a symbol to represent flux, the Greek letter, I guess that's phi. You can draw it this way or this way. So that's where we are now. So now I'm going to talk about the unit of flux. Well, one unit is called a Maxwell. A Maxwell. So I can have my flux symbol, phi, and the unit for that, one unit is a Maxwell. A Maxwell. And the way I would abbreviate that is, I might have 10 Maxwell would be capital M, lowercase x. So a Maxwell is a unit, and it turns out to be under here, the CGS, a Maxwell. What you want to remember is one Maxwell is equal to one line of flux. One Maxwell is one line of flux. So on the picture I have on the board, let's see what I have. Now remember, on the board, guys, what I'm doing, this board is a plane surface. So it looks like I'm drawing everything in the plane. But remember, this is three-dimensional. So this flux is actually like I'm showing it, but it comes around this way and goes into the board. So it's three-dimensional. So sometimes we live in the 3D world, but when we draw pictures, everything is flat. Well, you got to remember, this is three-dimensional. So it's coming out. This flux is coming out and going around into the board. But the way I have this drawn, I got 1, 2, 3. I got 6 lines. That means I have 6 Maxwells for the flux, which is silly. You would never have a magnet with 6 Maxwells, but I think the point is well taken here. So one unit for flux is the Maxwell, and it's a CGS unit. Well, there's another way to look at it. If I want a bigger unit, you know, when we talked about joules being energy, but a bigger unit of energy would be a kilowatt hour. So it takes so many joules to make a kilowatt hour. And the reason is, relatively, a joule is a small amount of energy. And so you wouldn't want your electric bill in joules. The paper would be this long. So they have a bigger chunk, the kilowatt hour. We'll say we'll let X number of joules be 1 kilowatt hour, and I can have numbers. I can deal with smaller numbers. Well, it's the same thing kind of here. The Maxwell represents individual lines, but then what they say is, all right, I'm going to let if I have 1 times 10 to the 8th Maxwells, I'm going to call that 1 Weber. This is the Weber. And WB. So the Weber, you want to remember this. I think on the practice sheet, we probably do something with this. I got a practice sheet up on Blackboard. You probably didn't have a chance to print it out yet, but when you print it out, I got some practice, but you'll see this. So here's a conversion you want to remember. 1 times 10 to the 8th lines, or 1 times 10 to the 8th Maxwell's equals 1 Weber. So that means a Weber is a bigger unit than a Maxwell. If it takes 1 times 10 to the 8th of these to make up one of these, that means a Weber is a bigger unit than a Maxwell. So it goes not over here, it goes over here for MKS. It's an MKS unit. So we got the Weber over here. Now if you wonder, well, why in the heck do we have 2? Was what I said before. If I'm measuring magnetic fields that are really, really, really small, like the Earth, you know, is a big magnet in space. It has a north and a south pole. It has a geographic north and south pole, and it has a magnetic north and south pole, right? So, but the Earth's magnetic field is relatively weak. So I probably would use, if I'm looking at these lines of force, I probably would use something small like Maxwell's. But if I had something really strong like the magnet on an MRI machine, I probably want to think about using something bigger like Weber, so my numbers will be a little smaller. So far, I got these lines of flux represented by this symbol, and the unit will be either the Maxwell or the Weber. And I gave you a conversion. If I got 1 times 10 to the 8th Maxwell's, that's equal to 1 Weber. That's where we are so far. Well, it turns out that the Maxwell and the Weber by themselves, that's not what's important. Here's what's important. Imagine I take a plane surface, usually 1 meter square, a meter by a meter, 1 square meter, and I stick that in there like that. So what I have is this. I want to keep that. So I got this plane surface like this. It doesn't have to be a meter by a meter, but I'll get to that in a second. But let's say I got that plane surface. That surface is an area. It's an area. It has an area to it. I can actually use this to figure out how much flux I have per unit area. Now, why would I want to do that? Because the more flux I have per unit area, the stronger the magnetic field. I mean, think about it. If these are lines of force, that's where my force comes from. I have 1, 2, 3 lines of force there. So I have this area. I have 3 lines of force here, right, per unit area. If I doubled that, so if I add 3 more to it, then I would have 6 lines of force per unit area. If I come up here, look at that. I got all of that flux going through that unit area. The same area, but more flux going through it. That's telling me the strength of my magnetic field. The more flux per unit area I have, the stronger the magnetic field. So there's a name for that. I'd like to erase this. There's something called flux density. Flux density, that's very important. The flux density is the amount of flux I have per unit area. So it's going to be flux per unit area. Now let me write this using symbols. For flux density, we use the letter B. B as in boy. So this right here, we use B for it. So B equals flux. Well, we use that for flux. And for area, we use A, like that. So this right here is flux density. I'm going to move this up and erase it so I can have more room. So what I had was B flux density equals B over A. Now, when you guys talk about the magnetic field, you say, oh, I got a magnet. It has a really strong magnetic field. You're not talking about flux. You're talking about this. You're talking about flux density. The strength of the magnetic field is referring to flux density. The more flux I have per unit area, the stronger the magnetic field. So when you talk about the magnetic field, that's what you're talking about. Now, what are the units for flux density? Well, for flux, we got the Maxwell or we got the Weber. So one way to do it is like this. If this right here is in Maxwell's, now remember, I'm over here, CGS. So if I'm using Maxwell's, that means for my area, I got to use centimeters. I got a square. That's 1 centimeter this way and 1 centimeter that way. So if I'm over here on the CGS, if I'm using Maxwell's, then this right here is in centimeters squared because I'm in CGS units. So one way to talk about the flux density is Maxwell's per centimeter squared. Remember when we did current? Remember when we said current is a coulomb per second, but we call that 1 amp? Or we said a volt was a joule per coulomb, we call that 1 volt. Or we said I can have a joule per second, but we call that 1 watt. Remember that? Well, if I have a Maxwell per cm squared, we're going to call that a Gauss. A Gauss. And use a capital G for Gauss. And since I'm using Maxwell's and centimeters, and that means that Gauss belongs over here on the CGS. So Gauss. Let me put that over there. So this Gauss, capital G, that's the unit for flux density if I'm in CGS. Or maybe I don't want to use Maxwell. Maybe I want to use Weber's. Well, I can do that. If I use Weber's for the flux, put Weber's there, then that means I'm over here because Weber, that's under MKS. And that when I do my area, then I'm going to have meters, so it's square meters. So if I have Weber's over meter squared, then that would be the unit for flux density under the MKS system, a Weber meter squared. But again, just like I did for here, I had a Maxwell per centimeter squared, we call it a Gauss. Well, I have a Weber per meter squared, we call that a Tesla, named after Nikola Tesla. So the Tesla, I can put that over here. The Tesla, that's an MKS unit. So basically, if I want to measure the strength of a magnetic field, I'm not talking about flux. I'm talking about flux density. And if I want to measure a really, really, really weak magnetic field, like the Earth's magnetic field is relatively weak, I'm probably going to use Gauss. If I want to measure a really, really strong magnetic field, like I gave an example about the magnetic field around like an MRI machine or maybe around your heart drive on your computer, a floppy disk that might have a strong magnet there. I'm probably going to use Teslas. Okay? So that's a lot. Well, I'm running out of time now. It's time to end. I got about 60 seconds left. So we did a lot. If you have your book, you probably want to start reading the chapter on magnetism. I'm only doing enough of this to do two things. Thing number one, the next device we're going to talk about is an inductor. And inductors, basically, they function using magnetism. So I want to be able to talk about inductors, and this is a good place to help us understand inductors. But there's a more important reason, though. This is the connection between DC and AC. So if you, I know some of you did actually sign up to take me for AC over the summer. It's going to be 10 weeks online. But we'll actually start with this stuff. I'll review some of this, and we'll get into some of we'll start with magnetism. So AC in Ron Singleton's class, AC in my class starts with magnetism. So this will be good to kind of segue our way into there, into magnetism. Now, I'm over a little bit, but just give me about one more minute. I want to say two things. Number one, so a lot of people, well, I won't say a lot of people, a few people missed the submission date for exam 2. There was a link, and I think I had the link where it closed out too early. I went in and I readjusted it. So some people emailed me their exam. The problem with that is I need that as a PDF, and I actually need that to go into Blackboard because I can open it up, I can mark on it, I can there's things I can do in Blackboard that I can't do when you email it to me. So I'm going to open that back up for you to, if you email me your exam, I'm going to open it back up and I'll send out an email. I'll open it back up this weekend. I'm not going to accept the email exam. You got to submit it in Blackboard. So for this one time, I'm going to open it. I'm going to open it back up. Some of you may have to get a penalty. Most people got it in on time, but some people, for whatever reason, I had all kind of reasons why people didn't get it in on time. So you may lose a couple points. I don't know. I have to think about that. But this next statement is important. Exam 3, probably on Sunday, but by Sunday I'm going to post exam 3, and I'm not accepting any late papers on exam 3. So the quickest way to get a bad grade in the course is to miss that date. So what I'm saying is exam 3, you cannot email it to me. I'm going to give you exam 3. You'll have like a week to do it. And it'll be set up to where you can upload it into Blackboard. But if you miss the submission date, the link will disappear, and I won't accept it by email. So no matter what, exam 3 has to be turned in, and it has to be turned in on time. I had one person say they were without internet or the internet wasn't working. Don't wait to the last minute. Usually I have those links set to expire at 11:59 p.m. on the day that they're due. So don't wait until that day. Get it done before. If you're still doing the exam, a half hour before it's due, then you're not doing what you're supposed to do. So I'm going to take the late exams for exam 2. I'm going to open up Blackboard again. I'll send out a announcement, and if you email me your exam, you need to upload it to Blackboard, and then I'll close it back out. But for exam 3, I'm not going to do that. I'll give you a due date, and you got to have it submitted to me in Blackboard by that due date, and do it before then in case you have some kind of technical problem. Your internet might be down, whatever. I had a lot of reasons why. It wasn't just one person. There was a lot of reasons why people didn't get exams submitted on time. So I'll make an exception this time. There'll be a small ding on your grade, nothing serious. But for exam 3, you got to get it in, and it's got to be in on time, or else you won't be able to submit it. Okay? Does anybody have any questions for me or comments before I end this session?
Yeah, for my lab, I thought I sent it through the computer, and I looked at it 5 minutes before the thing closed, and it didn't send, so I emailed it to you. Is that okay?
Yeah, just what I want you to do, Kevin, is text me, because the lab, I'm not going to mark the lab. All I'm going to do is read it. If it's right, you got 100 points. So, but just make sure you send me a text. Probably Sunday, you'll see Blackboard. I'll be grading. And when you see that, just send me a text. Say, hey, don't forget to put my exam grade in. The thing is, guys, I got my UC students are not, I think I get way more emails from Cincinnati State students. So I got all these emails with all these attachments, and it's some of everything. So it's just no way for me to keep track of all that. But if you upload the Blackboard, it goes right into a certain, and I know exactly what I got. So it's even safer for you to put it in Blackboard. That way, there's no way I can lose it through an email or whatever. So Kevin, what I want you to do is when you Sunday I'll be grading. When you notice that the grades are going in, just send me a text and say, hey, look for my email. And if for some reason I can't find it, I'll let you know. But I will definitely get your grade in there. That's okay. I'll work that out. But for the exam, okay, for the exam, I want those uploaded in the Blackboard directly because I want to write on those, and I can do that in Blackboard. Anybody else? Okay, well, if anyone else has questions, you got my number. You can text me or send me an email. If you email me, I probably won't see it until later tonight. If you text me, I'll see it in about 5 minutes. Or if you need any kind of workout session or whatever, I can always, like I said, I can. I'm not doing any exam problems. People ask me about exam. I'm not working any exam problems. You got to do that. But if it's some homework or you got questions, you want me to open up the camera, not record it, and we just do some. I don't mind doing that. The best time for that is during the lab period, though. But I have other times available. So if you're getting stuck on something. If you're taking me for AC, I'm probably going to do a lot of that because we're going to do that by remote. And AC is just it's like this stuff on steroids. I'm not trying to scare you, but there's a lot more to AC. And so I'm going to have time where I can open up the camera. We can have work sessions and that kind of thing. So we'll see how it works out. So if you have any questions that I haven't addressed or any concerns, send me a text or email, and I'm sure we'll take care of it. Guys, have a great rest of the day. Stay safe, and I will talk to you Monday.